So, you've got yourself a fancy new Raspberry Pi. How exciting! But now what? What are you going to do with it? Maybe you already have a project in mind. Maybe you plan on doing some research. Regardless, you're more than likely going to use the GPIO, the general purpose input-output ports. They are the little pins sticking out of the circuit board and allow you to plug various devices into your Raspberry Pi and, actually use it. Those little pins provide big power via input and output and encourage experimentation with a collection of interface standards such as SPI, I2C, serial, and one-wire. Don't know what I'm talking about quite yet? No worries. In this course, I'll walk you through those standards as well as the basics of connecting the Raspberry Pi GPIO to any device. I'll demonstrate a simple starting point with tips on how to avoid shorting out your Raspberry Pi. I'll also demonstrate advanced concepts for those of you with prior electronics experience. The Raspberry Pi GPIO is a great tool to explore the Internet of Things and to get started with microcircuitry. So, what are you waiting for? Let's put that Raspberry Pi to use. In this course, we'll play with electronics and the Raspberry Pi, but I don't expect you to know a lot about either. If at some point you're confused about the basics of Raspberry Pi, I'd encourage you to review the companion course in this library titled Raspberry Pi Essential Training. That will give you an understanding of how the Raspberry Pi works, how to install an operating system, and additional hardware you'll need to start it up. It will be helpful if you understand basic computer concepts such as input and output and memory and power. It will also be helpful if you have a knowledge of a programming language. I've kept programming simple and taken steps to make the intent obvious rather than optimizing code in ways that will make it more difficult to understand. If you understand concepts like variables and if-else statements, you should have no problem with the programs I'm writing in this course. As always, if you have any questions, I'd encourage you to post them in the Q&A section in the course. I'm notified when you post questions, and we'll try to answer them for you. In summary, you don't need advanced knowledge to gain benefit from this course, and I'm confident you'll find yourself surprised at what you've learned about electronics and the Raspberry Pi GPIO. This is a project course. That is to say, we're going to build things in the real world. So you'll need some hardware. First, you need a Raspberry Pi. Almost any Raspberry Pi will work. Be sure to get one with 40 pins rather than the original 26. The only Raspberry Pi that won't work is the original Raspberry Pi Zero without pins. For the purposes of this course, you don't need the fastest model. All the projects I've designed work just fine, even with the slowest Raspberry Pi. You also need a breadboard and jumper pins to make the connection of electronic circuits easier and cleaner. Finally, you'll need some inexpensive microcircuits. I've created a list of everything you need and the chapters you'll need them for. That list is in the exercise files. You'll also need a keyboard, monitor, mouse, and memory card. For details on these, consult the Raspberry Pi Essential Training course in this library. Overall, you can expect to spend less than $100 for all the equipment you'll need for this course, and quite possibly just a fraction of that amount. Let's start with a really simple demonstration of the GPIO. In this chapter, I'll show you how to connect a switch and an LED. When you're done, you'll have a bit of confidence about connecting to these pins and the beginning of an understanding of what they're for. In this project, I push a button to turn on the light. It's the simplest of all circuits, but it's enough to demonstrate how the Raspberry Pi GPIO works. There are 5 components: the switch, the LED, a 220 ohm resistor, a Raspberry Pi, and some jumper wires. The switch is connected to some input pins and ground. The LED is connected to an output pin, a resistor, and ground. Software running on the Raspberry Pi watches the switch. When the switch is on, the Raspberry Pi turns the LED on. Next, I'll show you how to create the circuit and write the software. Now, connect the green wire from the switch to the second pin from the left on the bottom row. Connect the black wire to the third pin from the left on the top row. Now for the LED. Notice that one leg is longer than the other. Carefully push the LED into the breadboard. Connect the long leg of the LED to the second pin from the right on the bottom row. Connect the short end of the LED to a resistor. Connect the resistor to the far right pin on the bottom row. Be sure to check your connections and make sure they agree with the wiring diagram I've provided. When you're certain everything is correct, go ahead and connect power to the Raspberry Pi. Nothing should happen. That's the job of software, and that's what we'll do in the next video. Without software, the Raspberry Pi is an inert lump of plastic and metal. So let's write some very simple software to watch the switch and change the LED accordingly. I'm writing this software using the Thonny editor that is provided with Raspbian, and I'll write the code using Python. First, I'll use the GPIO 0 module to connect to the LED and switch. And I need the pause command from the signal module. The GPIO 0 library allows me to create an LED object. I'll call it my LED. LED 26 indicates that I want to use GPIO 26 to control the LED. Then I'll do the same for the switch. I'll create an object called mySwitch and assign it to a button on GPIO 2. When those objects are created, I can test the LED. I'll use myLED.blink. Before you can run this code, add a pause at the bottom of the code. This keeps the code from terminating before the LED has a chance to blink. When I run this, I'll need to save it. I save this to my desktop, but you can save it wherever you'd like. I've included the final version of this code in the exercise files folder you can download from the LinkedIn Learning Library. If the LED doesn't blink, turn off the power, then reverse the LED leads. This is the most common problem. If reversing the leads doesn't work, check the jumper wires and connections to the GPIO. Also, check the resistor pins on the breadboard and that the LED actually works. Sometimes they do burn out. When you have the LED working, stop the code, comment out myLED.blink with a hash mark, and we're going to add 2 lines to incorporate the button. mySwitch dot when pressed equals myLED.on. These lines should go above the pause. Now this will connect the LED to the switch. Run the code, and now when you push the button, the LED will light up. There it is, the first project with the Raspberry Pi GPIO. This is a really simple project. Just a switch, an LED, and some software. But you've learned some really important things about the Raspberry Pi GPIO. First, you learned the mechanics of connecting circuits to the Raspberry Pi. Jumper wires and breadboards make experiments easy to set up and change. Hardware on the Raspberry Pi does nothing without software to control it. We'll learn more about writing software in future chapters. Third, you learn there is a difference between input and output. In this project, we used a simple input device, a push button, and a simple output device, an LED. In future chapters, we'll look at more complex input and output connections to the GPIO. Finally, you've developed confidence that you can use the Raspberry Pi to explore electronics and the Internet of Things. I've heard many people say they would like to experiment with the Raspberry Pi, but just never got started. So now, you're started. At this point, you might be wondering, we've only used a few of these pins, and what are the rest of them for? Let's explore that next. The Raspberry Pi is no different than any other computer, except it has a set of GPIO pins. Now, the Raspberry Pi GPIO is unique in several ways. First, the GPIO is physically easy to access. It's one of the first things you notice when you take the Raspberry Pi out of its wrapper. 40 pins stick up from the circuit board. You can't miss them. They are a standard configuration. It's called PATA, and you can purchase inexpensive adapters to fit over the pins. You can also use standard jumper wires to connect from these pins to a breadboard. Second, software control of the GPIO is straightforward. Raspbian, the default operating system for the Raspberry Pi, includes GPIO support for several programming languages, including Python, Java, and Scratch. The way those languages access the GPIO is clear. Sometimes, hardware access is obscured behind difficult-to-understand code libraries. But in contrast, the Raspberry Pi GPIO commands are built to be easy to understand. For example, here's a code sample to turn on an LED. You'll notice the purpose of the code is clear, even without additional documentation. Third, software control of the hardware is well documented. With past computers, I've accessed hardware with various languages, and I've always found it to be difficult because of obscure or missing documentation. For example, the Apple IIe hardware documentation assumed you understood Ohm's law and had soldering skills. Then you had to find documentation that explained how to access registers and the values required by the hardware, which is to say it was all very mysterious and required a lot of research. With the Raspberry Pi, I've always been pleasantly surprised at the easy availability of clear documentation. Finding the answer to an interface problem has rarely required more than a half hour of research. Fourth, there is a low cost of failure. Sometimes we make mistakes. I've shorted out pins, drawn too much current, or applied the wrong voltage. At least once that resulted in a dead Raspberry Pi, which cost me a total of $20. That's a pretty low cost for a worst-case scenario. In comparison, blowing out a PC or a laptop can cost thousands of dollars. Now, I'm not advocating that you seek to blow out your Raspberry Pi, but it is important to keep in mind the worst-case scenario is pretty acceptable. Finally, the GPIO voltages are safe. The Raspberry Pi GPIO uses somewhere between 3.3 and 5 volts DC, about the same as two AA batteries. You're not dealing with high voltages and currents you'll find in old television sets or photographic strobes. So you're not going to shock yourself if you accidentally grab the wrong wires. There's just simply not enough current or voltage available. In summary, The Raspberry Pi GPIO is designed for easy and safe experimentation. It provides a great workbench to launch computer-controlled electronics projects to explore the Internet of Things. Modern Raspberry Pis have 40 GPIO pins arranged in 2 rows of 20. So how do you make sense of all these pins? They aren't labeled, they all look the same, and it's impossible to simply explore them with a voltmeter to make any sense out of what they do. Let's take a look at the GPIO pins, starting with a chart I've supplied in every Raspberry Pi course. You'll find a copy in the exercise files included with this course. The handout is called 02_02_ GPIO pins. The graphic has 4 columns to the left of the picture and 4 to the right. The outermost columns on both sides are labeled function. This explains what those pins are for. Many of the pins on the GPIO are simply power or ground. I've identified all of these pins. They're useful for supplying voltages for circuits, testing, and other uses. They can also be the source of a short circuit, causing the death of your Raspberry Pi. Unlike any other pins, the power and ground pins cannot be turned on or off or reconfigured. Here I've highlighted the pins that provide 3.3 volts DC. If you used a multimeter to test voltages between one of these pins and ground, you'd read 3.3 volts. Here are pins that supply 5 volts. Again, if you test voltage between these pins and ground, you'll read 5 volts DC. Finally, the GPIO provides several ground pins. All of these could be connected with jumper wires to the ground rail of your breadboard. The remaining pins provide control signals or read input. All of them can be configured as simple input or output. In the previous chapter, we configured this pin to read the push button and this pin to light the LED. In addition, some combinations of pins can be used to provide specialized signals. We'll explore each of these connections in later videos, but these pins include I2C, which stands for Integrated Circuit. This is a common communication protocol used with many integrated circuits. Here's UART, or Universal Asynchronous Receiver Transmitter. This is a standard serial connection. SPI stands for Serial Peripheral Interface. This is a set of 3 signals plus 2 selector pins. It's similar to I2C in that it's commonly used to control microcircuits. The Raspberry Pi GPIO provides 2 SPI buses. These pins provide one-wire protocols, which is a less common interface, but only requires one data line to control multiple sensors. Pulse width modulation is implemented on several pins. Some pins provide pulse width modulation via hardware. All pins can provide pulse width modulation via software. These pins provide general-purpose clock signals. These can be set to output a frequency. Pulse code modulation is essentially the audio channel for the Raspberry Pi, but it's available for a digital to analog converter, or DAC. Pins 27 and 28 are always reserved for an ID EEPROM on the Raspberry Pi. Independently of which card you use, these pins are always reserved and should never be used to connect external components. That's a quick overview of how these pins are used, but actually using them will require a bit more explanation. In future chapters, I'll spend time with the advanced signals. For now, it's only important that you understand that these pins have specific functions. The GPIO numbering schemes are possibly the most confusing part of the Raspberry Pi GPIO. There are 3 ways to describe pins. Wiring Pi, BCM, and board. I'll be referencing the handout labeled 0202 GPIO pins. Here's an example. The top right pin of the GPIO can be described as BCM pin 21, GPIO 21 board pin 40, or wiring Pi pin 29. So let's spend a bit of time understanding these different numbering schemes. First, let's talk about wiring Pi. This development library has been around for several years, but has recently been deprecated by its author. You will continue to see code written using this library, but moving forward, you should use a different library. It's more likely you'll encounter the BCM numbering scheme. BCM is available for most languages, including Python and Scratch. BCM is the numbering scheme used when you see GPIO. For example, GPIO 17 is found on the 6th pin from the lower left corner of the Raspberry Pi GPIO. Finally, there's also the board numbering scheme. This identifies the physical location of the pin on the Raspberry Pi. As an example, the first pin on the inner left is pin number 1. The last pin on the outside right is pin number 40. For a minute, take a look at how board numbering compares to BCM numbering. In this example, I'm referring to identical pins. The LED is connected to the same pin. Under board numbering, that pin is referred to as pin 37, but under BCM, the same pin is referred to as GPIO 26. Board numbering is becoming increasingly rare. The only time you're likely to see it is with Python or documentation. In this course, we'll be building projects. That means connecting electronics to your Raspberry Pi GPIO. The most common way to do this is with a breadboard and jumpers, but you can also use wire wrap, breakout headers, and even soldering. Some are acceptable and have advantages. What I don't recommend is soldering electronics directly to the GPIO. In some cases, this may work, but directly connecting to the GPIO pins is for advanced development. So let's first talk about using a breadboard. Get a breadboard with a blue and red line across the outside edges. The red line of holes can be used to supply a common 3.3 volt DC, and the blue line of holes can supply a common ground. To connect from the Raspberry Pi GPIO, you'll need jumper wires. One end should be female, and one end should be male. You'll also need some male-to-male jumper wires to connect between points on the breadboard. You'll also want to connect the blue line of dots to a ground pin on the GPIO. It doesn't matter which Raspberry Pi GPIO ground pin you use, but as a suggestion, connect pin 39, then use a male-to-male jumper to connect from one blue rail to the other. Now you have easily accessible ground lines for your circuits. Black wires customarily indicate ground. Likewise, connect a 3.3 volt DC line from GPIO to the red line. If you have it, use an orange wire to connect the 3.3 volts. You may also want to connect a 5 volt DC line to the other red line on the breadboard. For 5 volts DC, a red line is commonly used. The red and blue lines are the same across the length of the board. So this hole provides the same voltage as this hole. In the center, Connections run from side to side instead of end to end. So this hole is the same connection as this hole. Integrated circuits should be placed across the gutter of the breadboard. Then jumper wires can be connected along the lines of the legs of the circuit. There is also a commercial solution to connecting the GPIO to a breadboard. This device is called a breakout header. It's simple to use. Connect one side to the GPIO. Be careful to place it correctly. There should be instructions on how to identify which side is pin 1. Connect the other end of the breakout to the breadboard, being careful to bridge across the gutter. Now you can use male-to-male jumper wires to connect between the Raspberry Pi and other components on the breadboard. Breakout headers provide an uncluttered connection between GPIO and breadboards, but may be bulky and provide more connections than necessary. Another option is wire wrap, but that's rare and requires a special tool. In summary, you have several options for connecting electronics to the Raspberry Pi GPIO. Breadboard and jumper wires, breakout headers, which are easy but bulky, wire wrap, which is slightly more permanent, and soldering, which is permanent but runs the risk of melting components. Which method you choose will depend on your skills and needs. The Raspberry Pi GPIO is more than a bunch of indiscriminate pins. Many of them have special purposes, and in this chapter I'll show you how to use the one-wire protocol and pulse width modulation. The one-wire protocol is an ingenious way to send low-speed data across one wire. Provide it with voltage and ground, and the data flows across the one signal wire. In addition to one wire, this project uses pulse width modulation. PWM, or pulse width modulation, simulates an analog signal by pulsing a digital signal. There is an excellent description of pulse width modulation in this library, but simply put, it's a way to use a digital signal to emulate an analog value. The project we're building uses several DS18B one-wire temperature sensors connected to an analog voltage meter. If we change the temperature of one of the probes, the Raspberry Pi recalculates the average temperature and changes the pulse width modulation value to the analog meter. Let's break this project into parts: the temperature sensors, the meter, and the software. All right, let's get to it. First things first, we get to build a circuit. And before building any circuit, be sure to turn off the power to the Raspberry Pi. In the next two videos, I'll show you how to build the one-wire and pulse width modulation project. And I've included a shopping list as part of the exercise files. This is a fairly easy circuit to connect. In this video, I'll focus on the one-wire connection to the DS18B20. To start, connect pin 1 of the Raspberry Pi to the red or positive voltage of the breadboard. This supplies 3.3 volts to the power rail. Now connect pin 39 of the Raspberry Pi to the ground rail. Take a look at the DS18B20. There are 3 wires. In some one-wire devices, you'll only have 2 wires, signal and ground. You'll find the implementation of the one-wire specification varies from device to device, so you'll want to do a bit of research and prototyping before you commit to manufacturing. To start, I'm going to connect the DS18B20 to the breadboard. I've spread the 3 wires out, red, black, and yellow, to give me some extra room to work. Use a red jumper wire to connect the red DS18B20 wire to the voltage rail on the breadboard. Use a black jumper wire to connect ground to the black wire on the DS18B20. For the one-wire signal, connect pin 7 of the Raspberry Pi to the DS18B20 signal wire. Pin 7 is also known as GPIO 04. The Raspbian operating system has built-in support for the one-wire data protocol and assumes that if there are one-wire devices, they are connected to pin 7. Finally, connect a 10K resistor between the DS18B20 signal pin and 3.3 volts DC. This is known as a pull-up resistor and ensures the signal pin is in a constant state. You may also hear about pull-down resistors, which perform a similar function. I now have two DS18B20s connected to the Raspberry Pi. Before we can go any further, there's a bit of software configuration to be done, so power up the Raspberry Pi. You'll need to enable one-wire, and to do that, you'll use raspi-config from the Raspberry Pi menu. Go to Preferences, Raspberry Pi Configuration, select the Interfaces tab, and enable one-wire. Hit OK and reboot. You can check for the presence of the one-wire devices. Open up a terminal window, and then cd to /sys/bus/w1/devices and list the devices. What you'll see is W1 underbar bus underbar master. That you don't care about. What you do care about is the listings that start with 28, and you'll have a directory starting with 28 for each one-wire device. If you look inside of one of those directories by using ls, and we can type in ls28-011fa05, and that will list that directory. And inside the directory, you'll see several other subdirectories and files executable. What you really care about is the w1 underbar slave, and we can cat that file. So let's cat 28-011-0557/W1. And this is the actual reading from that one-wire sensor. The important part of this particular sensor is it returns the temperature in the lower corner. Divide this value by 1,000 and you'll have the centigrade degrees. So we've now installed two one-wire sensors and confirmed that they're actually appearing to the Raspberry Pi. In the next video, let's install an analog meter. In this video, I'll show you how to build the pulse width modulation part of this project. I assume you've already connected the DS18B20 to the breadboard. Now position the meter next to the breadboard. It helps to use a bit of double-stick tape to keep it in place. Connect the meter ground to breadboard ground. Then connect a jumper to pin 37 of the Raspberry Pi. Bring that out to the breadboard and connect the other side of the meter to that jumper. So in other words, connect the other side of the meter to signal pin 37 of the Raspberry Pi. This pin is also known as GPIO 26. Now, any GPIO pin can supply pulse width modulation, but some are driven by hardware and require less processing time from the CPU on the Raspberry Pi. In reality, it doesn't make a lot of difference which pin you use. Only applications that require extremely fast signals require dedicated hardware. And that's all it takes to connect the meter. let's write some software. In the previous videos, I showed how to connect the DS18B20 and meter to the Raspberry Pi. In this video, I'll describe the software that collects information from the sensor and displays it on the meter. Use Thonny to open 03_04 readtemp.py in the example files. Push the Run button, and you should see the readout from any connected DS18B20 in the console. If you're looking at the meter, you should also see that move to reflect the average of all the DS18B20 readings, and we'll look at that in a minute. First, let's take a look at the code that makes all this happen. In line 4, you'll notice that I'm using Python with the rpi.gpio library. I'm using rpi.gpio instead of GPIO0 because GPIO0 doesn't support one-wire. In lines 13, 14, and 15, I set up GPIO26 as a pulse width modulation output. I'll discuss duty cycle and frequency in a later video. For now, understand that duty cycle affects the simulated voltage. In line 18, I define a helper function called getTemps, which returns a list of temperatures from all available DS18B20 devices. These appear in the one-wire directory as directories starting with 28. Starting in line 33, I've created a function to map the temperature coming from the DS18B20 sensors to a range from 0 to 100. The temperature range coming from the DS18B20 is anywhere from -55 to 125 degrees centigrade. The maximum value I can put out through the PWM pin is 100. So this function takes a value from the DS18B20, clips it to a range between 5 and 50 degrees centigrade, and then maps it to a range of between 0 and 100. In line 47, the program uses a try loop to retrieve values from the temperature sensors. Retrieved values are printed to the console and output to the meter using pulse width modulation duty cycles. Finally, in line 58, I handle the keyboard interrupt, a Control-C, to clean up all of the GPIO pins. I can demonstrate the sensor with a cup of ice water and a cup of tea. Run the program. Let's enlarge the console a little bit. And you can see that we're getting values from the DS18B20s. Let's take one of those sensors and dip it in the tea. You'll notice the values change immediately. This is reflecting the increase in temperature for the first DS18B20 that I put into the tea. You'll also notice that the meter has changed its position. Now I'm going to take a second DS18B20 and dip it into the ice water. You'll notice a change in the values displayed on the console, and you'll notice a change in the average PWM, which is the average of both sensors available to us. One sensor is high, 35 degrees centigrade. One sensor is at 7 degrees centigrade. This demonstrates the use of one-wire sensors coupled with pulse width modulation to drive an analog meter. In this project, you learned about several concepts. Let's review them. We used the one-wire protocol to communicate between the Raspberry Pi and DS18B20. This is a really simple protocol that only uses one GPIO data pin. It can be used over long distances, possibly 200 meters, and is inexpensive to implement. On the downside, this protocol is fairly slow, but in many cases, this speed isn't really a factor, especially if you're using Python with the Raspberry Pi and Linux. In this project, I use pulse width modulation to control the meter. Pulse width modulation is an easy way to simulate analog signals and can be done with hardware or software, and is the only way the Raspberry Pi can generate any sort of analog signal. On the downside, pulse width modulation isn't really an analog signal. If it's being used with a device that can respond quicker than the signal is pulsed, it will result in a blinking effect. The DS18B20 is an inexpensive sensor that provides temperature data. It uses a one-wire interface, it only reads temperature, it only costs about $2, and the accuracy is plus or minus 0.6 degrees centigrade. Finally, there are a couple of important concepts illustrated with the use of Python. First, I had to resort to the rpi.gpio library to interface between Python, the GPIO pins, and one-wire. There are other libraries such as GPIO 0, but in this case, rpi.gpio provided us with a deeper level of control and access to one wire. The only downside is that you might not be used to working with rpi.gpio. Perhaps you use a different language, such as Scratch or C. In any case, Python is a language you'll find useful and easy to learn once you get started. Pulse width modulation is frequently used with the Raspberry Pi, and there are some tricks to using it efficiently. It's worth our time to look at pulse width modulation in depth. Pulse width modulation is a method to simulate a variable analog signal with a digital signal. For example, consider an LED. It can only be turned on or off. Pulse width modulation is used by dimmers to turn LED room lights from off to middle brightness to fully on. Pulse width modulation works by rapidly turning a digital signal on and off, faster than the device can respond. If the digital signal is always off, the light will appear off. If the digital signal is always on, the light will appear on. If the digital signal is only on half the time, the light will appear to be on at half brightness. There are two controls for pulse width modulation. The first is signal frequency. This is how quickly a signal switches on and off. If you're using pulse width modulation to control a water heater, the frequency can be fairly slow, say once every second. If you're using pulse width modulation to control an audio speaker, the frequency must be fast, thousands of times a second. In this slide, the top row of bulbs switches between on and off more frequently than the middle row. The second control is called duty cycle, and it controls how long a signal is on compared to how long the signal is off. If a signal is on 50% of the time, like the top row, the light will be on at half intensity. If the signal is on at 75% of the time, like the second row, the light will be on at 75% intensity. The longer the duty cycle, the brighter or stronger the perceived signal. I've included a project that demonstrates the effect these two variables have on pulse width modulation. Build the circuit as described in 03_06 pwm_demo.py and run the code. This allows you to move the mouse and change both frequency and duty cycle. The speaker and LED will reflect the changes you make. In the Python code found in 03_04 readtemp.py, the frequency was set to 50 Hz, and you can see that on line 14. In line 55, you can see that the duty cycle was changed according to the temperature. As the temperature went up, the duty cycle also went up, and the meter needle moved further up the display. On the Raspberry Pi, pulse width modulation is available for Python with the rpi.gpio and GPIO 0 libraries. It's not available for Scratch. Pulse width modulation is implemented on several pins. These two pins provide pulse width modulation via hardware. All pins can provide pulse width modulation via software. In most cases, you'll never notice the difference between hardware pulse width modulation and software pulse width modulation. In this project, we use the one-wire data protocol to work with temperature sensors. This protocol isn't in common use, but you may find it in certain applications. The one-wire protocol is an ingenious way to send low-speed data across one wire. All you have to do is provide it with voltage and ground, and then the data can flow across that single additional wire. There are a few other things you'll want to know. Let's break these out and look at the details. I've mentioned that one wire is low speed. By low speed, I mean it can gather and transmit data somewhere between 16 and 64 kilobits per second. In comparison, a standard serial port can provide 25 megabits per second, or the equivalent of about 25,000 kilobits per second. That might seem unusable, but keep in mind we're using this with a Raspberry Pi running Raspbian, a Linux operating system. Linux generates frequent interrupts and is generally a bad choice for real-time data acquisition. Throw Python on top of that, as well as the need to calculate averages and run a display, and you'll find that one wire can provide data faster than the Raspberry Pi can consume it. This protocol is named one wire, but that's a slight misnomer. A one-wire device requires 3 wires, possibly 2 if the device includes a battery or a capacitor. The most important wire carries a signal. This is used to send positive and zero voltages to the receiver. There is also a ground line. This is essential since you can't have a positive voltage without a reference voltage, or no voltage. That reference is supplied by the ground wire. Finally, the device needs some sort of voltage to operate. This voltage, usually 3 to 5 volts, can be supplied by a third voltage line or by an onboard storage device such as a capacitor or battery. This battery or capacitor can be charged from parasitic power. Parasitic power is a way to reduce the number of wires to the one-wire device by removing the need for dedicated power. It starts with an onboard battery or capacitor to store power for the one-wire sensor. This power is taken from the data signal line. When there is a positive signal, the signal line has positive 3 volts. Part of that 3 volts can be used for communication, and part of the 3 volts can be used to charge the battery, which is fine as long as the data line is positive. But if the data line goes to 0, there is no voltage and the battery or capacitor can't be charged. Likewise, if there are several one-wire devices connected and they are all pulling parasitic power, there may not be enough voltage to charge capacitors and carry signals. One of the advantages of one wire is the long distance sensors can be located from the computer. Several sources on the internet indicate one-wire devices can be run over wires of 200 meters. The official documentation is a little bit less encouraging. According to the spec and electronics, the voltages used across the data, signal, and ground wires are sensitive to several factors, including the resistance of the wire, the number of devices, how those devices are arranged, and how much wire is actually used. The actual distance will depend on all of those factors. Before committing to a long-distance one-wire network, it would be best to prototype and test. Finally, be careful with devices advertised as one-wire, as the implementation may be different than expected. For example, some devices do not allow networking, and many don't provide for parasitic power. The Raspbian operating system has built-in one-wire support and assumes that one-wire devices, if connected, are always connected to board pin 7. If you can use one-wire devices in your application, they're cheap, they're easy, they're long distance, and it may be just exactly the answer you're looking for. In a previous chapter, we buzzed through an overview of the GPIO pins. Let's do a deep dive on GPIO input pins. Raspberry Pi inputs are digital. That is to say, they only understand on or off. To signal on, feed an input pin with 3.3 volts DC. To signal off, feed it 0 volts DC. There are no analog to digital pins available on the Raspberry Pi, although there are integrated circuits that can be used for this purpose. Be careful about the voltage you feed a Raspberry Pi input pin. Design your circuits to produce no more than 3.3 volts DC and no less than 0 volts DC. If you're getting close to 5 volts or above, you run the risk of burning out your Raspberry Pi. In an upcoming video, I'll describe the use of Zener diodes to prevent this. Finally, input pins can be configured to generate interrupts, although this is language specific. In a future video, I'll describe how to implement GPIO interrupt functionality with different languages. You may have heard of pull-up and pull-down resistors and how they need to be used with Raspberry Pi inputs. It's helpful to understand what they are, how to use them, and when to use them. In this illustration, there is a pull-down resistor between the switch and the ground located on the same side of the switch as GPIO 06. We can ignore the second resistor between the switch and a 3.3 volt DC. It's only there to prevent a short circuit. This pull-down resistor appears to bypass the switch by creating a circuit from GPIO 06 through the resistor to ground, but that's not what it's doing. Instead, the pull-down resistor pulls the voltage to 0 until the switch is closed. At that time, 3.3 volts DC flows through the switch. A small part of that voltage goes to ground through the resistor, but a majority goes to GPIO 06, signaling to the Raspberry Pi that the switch is closed. The entire purpose behind pull-down and pull-up resistors is to prevent digital circuits from floating, which is an unknown state. Is it on or is it off? Digital circuits are binary. 0 volts is off. 3.3 volts is on. Anything in between is floating. It's uncertain. Pull-up resistors create a positive signal, a value of 1 or on or 3.3 volts. Pull-down resistors create a 0 signal, a value of 0 or off or 0 volts. When building circuits with the Raspberry Pi, pull-up resistors should be between 10,000 ohms and 100,000 ohms. The value doesn't matter all that much, assuming you're not creating complex circuits. Pull-down resistors are somewhere between 200 and 50,000 ohms. The default is 50,000. The Raspberry Pi has built-in pull-up and pull-down resistors. Unless you reconfigure them, GPIO pins from 0 to 8 default to pull-up. GPIO pins from 9 to 27 default to pull-down. Surprisingly, all of this pull-up and pull-down is already handled by some programming languages. Let's start with Python and the rpi.gpio library. I'm looking at 04_02 pull-up pull-down underbar rpi gpio.py. In lines 9 through 12, I've configured 4 pins for input. On the Raspberry Pi, these pins are disconnected from any circuits, so this program will read the raw values. Notice in line 9, I've included pull up down equals gpio.pud underbar up. In line 10, I've included pull up down GPIO.PUD underbar down. The Raspberry Pi has built-in pull-up and pull-down resistors activated by these commands. In addition, there are default states. In line 11, I've relied on the default for pins 0 through 8 as pull-up. In line 12, I've relied on the default for pins 9 through 27 as pull-down. Run the code, and you'll see the raw value of these pins. Note that the default pull-up pins register as pushed, and the pull-down pins register as not pushed. Now look at 04 underbar 02 underbar pull-up down underbar GPIO 0.pi. It's the same code, but written with the GPIO 0 library. Run the code and notice that all pins register as not pushed or off. This is a default for the GPIO 0 library. I've also created a scratch version, which you'll find in 04 underbar 02 underbar pull up down underbar scratch. Scratch doesn't provide a way to specify pull up or pull down. When you run this code by clicking on the green flag, it indicates that Scratch pulls all pins up by default. In summary, pull-up and pull-down resistors are important and can be done with hardware or software. If you're relying on software, not all languages handle the defaults the same. For the most part, software defaults and the Raspberry Pi will make reasonable choices for these values. But in some cases, you'll want to know why these choices are being made and how they're being made. The Raspberry Pi GPIO can only handle 3.3 volts. It's important to restrict voltage to that level. Much more voltage will turn your Raspberry Pi into mush. In this hypothetical example, I'm using a solar panel as a sensor. It puts out 5 volts, more than the recommended 3.3 volts for a Raspberry Pi. So we need to reduce the 5 volts to 3.3 volts. There are two ways to fix this. One is with a resistor, another is with Zener diodes. Let's check out the resistor method first. It's a technique called voltage dividing. For a complete discussion of voltage dividers, I highly recommend watching Voltage Dividers from Barenstone's Electronics Foundation's Basic Circuits course in this library. In a voltage divider circuit, two resistors are used to divide the voltage between the Raspberry Pi and ground. These resistors are typically labeled R1 and R2. To calculate the proper values of the resistors, you also need the source voltage and the desired voltage. Here's a slide with a diagram of what the circuit will look like. Notice the placement of resistor 1 and resistor 2. The easiest way to calculate this is with an online calculator. Search the internet for voltage divider calculator. Now, when you get a result, there is more than one correct solution, since the resistors need to be a ratio rather than an exact value. In this example, the source voltage, or voltage in, is 5 volts DC, so I place that in the formula. I also replace V out with the desired voltage of 3.3 volts. Using the calculator, the equation yields two resistor values, 220 ohms and 470 ohms, which is approximately a 1/3 to 2/3 split. Now, these are standard resistor values, and V out will actually be about 3.4 volts, but that's within tolerance for the Raspberry Pi. The smaller resistor connects to the solar panel and the 5 volts it supplies. The other side of that resistor connects to the GPIO and the second resistor. The second resistor connects to the incoming signal line. The other side of that resistor connects to ground. Now, let's take a look at another solution using Zener diodes. Zener diodes are specially built to open a channel for excess voltage. They are ranked for different voltages, so if you have a 3.3 volt Zener diode connected to ground, anything above 3.3 volts is shunted away from the Raspberry Pi. Very convenient. For an in-depth discussion of Zener diodes, I recommend the Zener diode segment of Stone's Electronics Foundation's semiconductor devices. Let's take a look at a real-world example. What you're looking at is a demonstration circuit of how a Zener diode can protect the Raspberry Pi from overvoltages. I have 5 volts coming into the breadboard. I have a 22 ohm resistor, a push button, and a voltage gauge. When I push the push button, you can see that I apply 5 volts. That 5 volts is being measured at the far end of the resistor. Now I'd like to connect the Raspberry Pi to that signal so I can tell when the push button is pushed, but 5 volts is going to blow out my Raspberry Pi, so I'm not going to connect it just yet. Instead, I'm going to change this circuit just a little bit. I'm going to include a Zener diode in this circuit. I've already placed a Zener diode on the breadboard. I'm going to ground the anode side of the Zener diode. I'm going to move our measurement point from the resistor to the cathode of the Zener diode. And then I'm going to patch from the resistor to the cathode side of the Zener diode. Now when I push the button, you'll notice that the voltage has been reduced to 3.3 volts, which is safe for the Raspberry Pi. I can now connect the Raspberry Pi to the signal on the cathode side of the Zener diode. Serial Peripheral Interface, known as SPI, is a common interface protocol used to communicate between computers and integrated circuits. SPI depends on 4 signals: MOSI, which stands for Master Out, Slave In; MISO, which stands for Master In, Slave Out; SCLK, which is a serial clock; and CS, sometimes CE, for chip select. SPI depends on several timed events initiated by the chip select and timed by the serial clock signal. Each pulse from the clock sends information from the master to the slave, MOSI, and from the slave to the master, MISO. SPI allows multiple devices on the same data bus. Each device can share the same voltage, ground, MOSI, and MISO and clock signals. Each device has a unique, private chip select. This is the only line that isn't shared and is used to decide which chip is allowed to communicate over the data bus. In this project, I'll demonstrate how to work with 2 SPI devices on the same data bus. I've chosen 2 popular devices, the BME280 environmental sensor and an OLED 1.5-inch square display. Both use the SPI communication protocol. The BME280 is a chip with sensors for pressure, humidity, and temperature all in one package. It supports I2C and SPI interfaces. The second device is a small color display, only 1.5 by 1.5 inches. This device only supports SPI communication. However, we'll see in a minute how it defines SPI somewhat differently than the standard. In this session, I'll walk you through the steps necessary to connect and program the BME280 environmental sensor. The sensor looks like this. There is a chip with wires. There is no display on the BME280. I've included a handout in the example files with a table instructing how to connect the BME 280 to the Raspberry Pi GPIO. Here's a snapshot from that handout. Note that chip select goes to pin 36. This isn't listed as an official SPI chip select, but this doesn't matter, since the chip select pin only has to supply a binary voltage. Any GPIO output pin will work. Fully connected, it looks like this. There's a lot of wires, so I've placed a piece of paper on the breadboard identifying the SPI signals. When you've connected all the wires and double-checked your connections, restart the Raspberry Pi. When your Raspberry Pi has rebooted, you'll need to check the SPI dev is available. To do that, open up a terminal window. I'll maximize it. Type in lsmod and a vertical bar followed by grep for SPI. You should see SPI dev. If you don't, you're going to need to install it. Here's how to do that. First, type in sudo apt-get update. Then type in sudo apt-get install python-dev. Type in git clone git://github.com/doceme/py-spidev. In my case, this is already existing, so I don't need to run this. If you don't already have this directory, git clone will create the directory for you. cd to the new directory. It's called py-spidev. And then sudo python setup.py install. You'll also need to enable SPI. To do that, go to the Raspberry Pi menu, Preferences, Raspberry Pi Configuration, Interfaces, and make sure that SPI is enabled. Click on OK, and then reboot. When your Raspberry Pi is up and running, you can test the BME 280. To do this, open up a terminal window, cd to the exercise files. In my case, I've placed them on the desktop in exercise files. You'll find Chapter 5, and in Chapter 5, you'll find 0502 BME Environmental Sensor Demo Code. In that directory is a command called BME280, and you can run it by typing in sudo./BME280. Running that command will read information from the BME280 and display it on screen. You'll notice there are 3 sensor readings: temperature, barometric pressure, and humidity. You should see a repeating line of temperature, barometric pressure, and humidity. Reality check those values. If they're impossible, say 80 degrees centigrade, check your connections between the Raspberry Pi GPIO and the BME 280. With the BME 280 running, try holding the sensor in your hand to warm it up. Or possibly breathe on it to change the humidity. The BME 280 is a great demonstration of both SPI and the amount of sensors available in a very small package. In this session, I'll walk through the process of connecting and testing the 1.5-inch RGB OLED. This OLED, or OLED for short, looks like this. There is a display with several colored wires. If there isn't a display, it isn't the correct part. I've included a handout in the example files with a table instructing how to connect the OLED to the Raspberry Pi GPIO. Here's a snapshot from that handout. Don't remove the BME280 from your breadboard. The OLED will connect just fine alongside of it. In fact, note that the MOSI, voltage, ground, and clock signal lines are shared between the two integrated circuits. You'll also note that the chip select, or chip enable, is on a different pin than the chip select for the BME280. Each SPI device uses a private chip select pin to determine which device gets to control the data bus. You may also note there isn't a MISO connection. MISO stands for Master In, Slave Out. Since a display doesn't send data back to the master, there isn't a need for a channel from the slave to the master. Therefore, there is no need for MISO in this circuit. You'll also notice there are two additional lines, data/command and reset. These are not part of the SPI specification, but used specifically by this OLED display. Fully connected, it looks like this. That's a lot of wires, so I've placed a piece of paper on the breadboard identifying the SPI signals. When you've connected all the wires and double-checked your connections, restart the Raspberry Pi. Now you can test the display connections. Go into the exercise files, open Chapter 5, look inside the 0503 OLED display sample code, and start main.py. Go ahead and run that code. You should see a colorful display. If you don't, double-check the connections to the Raspberry Pi. Let's look back over the previous two sessions. What exactly did you learn about SPI and the Raspberry Pi? We've seen how the Raspberry Pi implements SPI, providing two SPI channels with two or more chip selects per each channel. We've also seen how chip select signals can be supplied from any GPIO output pin. It doesn't have to be one of the chip enable lines identified as part of the SPI implementation. Most obviously, you saw SPI in action, and you have an understanding of the different signals that make up the serial peripheral interface communication. SPI allows multiple devices on the same data bus. Each device can share the same voltage, ground, MOSI, MISO, and clock signals. Each device has a unique private chip select. This is the only line that isn't shared and is used to decide which chip is allowed to communicate over the data bus. SPI seems to be a well-defined communication protocol, but we found that's not the case. First, the SPI hardware implementation can be different from module to module. In the two modules we experimented with, the OLED and the BME280, there were different acronyms, different color wires, and additional or missing signals. This makes SPI more difficult to explain and document. Second, SPI only describes how the hardware will communicate. It does not describe the messages being exchanged or restrict how the chip reacts to SPI signals. As an example, the BME280 chip doesn't take a weather reading until the chip select goes low, at which time there will be a 40 millisecond delay. Trying to read the weather too quickly will result in erroneous values. Third, SPI modules frequently require accompanying libraries. In our case, the BME280 library was written in C. The OLED display was written in Python. You may find other SPI device libraries written in C++, Java, or other languages. So before you commit to an SPI module, Check to see if there's a library that supports this chip and in a language you can use. Remember that the BME280 library is written in C and the OLED device driver is written in Python. You can use a C library in Python, but that's an advanced skill and you'll need to do some research. Be aware of that issue and avoid buying a device that won't work without serious modifications. Second, hardware implementation may vary. The OLED display omitted the MISO signal but added a reset and data command signal. The BME280 provided a standard collection of signals. Plus, the chip select colors weren't consistent across the two devices. There is nothing preventing manufacturers from creating their own color schemes, so be aware of the potential for implementation differences. Third, SPI does not dictate the messages exchanged or the protocol. In the case of the BME280, when CS went low, the chip was selected, and that was a signal for the chip to start sampling the weather. In the case of the OLED, if the chip select went high, the display continued to show the latest graphic or text, even though it wasn't an active SPI device. Different manufacturers will assume different meanings for the signals, and be aware there may not be consensus across the industry. The serial peripheral interface is well defined on a hardware level, even if it tends to wander on the software side. Understanding how SPI signals work will help implement projects and debug related problems. So let's take a deep dive into SPI. There are two lines used to exchange signals between the Raspberry Pi and an SPI module, MOSI and MISO. These are acronyms for Master Out, Slave In, and Master In, Slave Out. In our case, the Raspberry Pi is the master. The BME280 or OLED display are the slaves. Chip Enable or Chip Select or Slave Select are all names for the same signal. Each slave is tied to a Raspberry Pi GPIO pin. When the Raspberry Pi drops the pin voltage to 0, that particular chip is enabled and allowed to communicate over MOSI or MISO. At a low level, SPI depends on several timed events. First, the master, in this case the Raspberry Pi, sets the chip select signal from high, a positive voltage, to low, which is a voltage of 0. This is a signal to the slave device to begin communication over the SPI bus. In our case, the BME280 or OLED display are slave devices. Remember that each slave device has a unique chip select pin. When the chip select goes low, the serial clock provides a timed signal. This clock signal controls the beginning and end of the data bits passed between master and slave devices. Timed by the clock signal, the MOSI signal will send serialized data to the slave. One bit will be passed on each clock pulse. That bit can be either 0 or 1. At the same time, the slave will communicate back to the master over the MISO line. Since the MOSI and MISO lines are separate, the master and slave devices can communicate simultaneously. Because this communication is timed by the clock, it's known as synchronous. When the communication is finished, the master, the Raspberry Pi, returns the chip select to high. This is a signal to the slave to stop communicating over the MOSI and MISO lines. The Raspberry Pi has one hardware-based SPI implementation, although additional SPI channels can be implemented through software. The hardware-based SPI implementation uses the pin assignments shown in this slide. In this chapter, the BME280 chip select was done through BCM16. In this graphic, you'll note that chip select is either BCM08 or BCM07, not BCM16. In spite of this, it worked, and demonstrates that chip select can be done with any Raspberry Pi GPIO pin. But heads up, If you're using the GPIO 0 library for Python instead of the rpi.gpio library we used in the OLED example, the GPIO 0 library implements SPI with the assumption of chip select on BCM 08 and BCM 07. The OLED display was also connected to SPI 0, sharing MOSI and MISO with the BME 280. However, the OLED display was connected to chip select 0 on BCM 8. For those of you that enjoy pushing limits, there is a second SPI interface available, assuming you have 40 pins and using Raspbian Jessie or later. You'll also need to edit bootconfig.txt, and you'll need to use the Pi GPIO library instead of GPIO 0 or rpi.gpio libraries. Be warned, use of the auxiliary SPI channel is an advanced topic. Raspberry Pi pins are digital. That is to say, they only understand on or off. If a pin supplies 3.3 volts DC, it's considered to be on. If a pin has 0 voltage, it's off. There are no analog output pins available on the Raspberry Pi, although there are integrated circuits that can be used for this purpose. We've also talked about simulating analog with pulse width modulation, but that's not true analog. The GPIO pins can't supply any more than 3.3 volts DC. There are pins that can supply 5 volts DC, but they aren't controllable. The 5-volt DC pins are always on. Be careful about the current you pull from a Raspberry Pi output pin. GPIO pins should only be asked to supply less than an amp. Much more than that, and you risk frying the Raspberry Pi. If you're unclear on the difference between voltage and current, I highly recommend the voltage and current chapters in Barenstone's Electronics Foundation's Fundamentals. Here's a chart that shows the power capabilities of a Raspberry Pi versus the power requirements of various household appliances. For example, the Raspberry Pi with the green triangle can supply somewhere between 0 to 1 point something amps. A vacuum cleaner can use up 6 to 9 amps and would be a bad idea to plug into a Raspberry Pi. Note that anything other than an LED falls well outside the limits of the Raspberry Pi GPIO. To summarize, Raspberry Pi output pins are digital, not analog. They supply a maximum of 3.3 volts DC and restrict current flow to less than 1 amp. Protecting the Raspberry Pi output pins is a matter of preventing too much current from being drawn through the GPIO. This could happen, for example, when you might be controlling a motor. There are 2 ways to protect against this: a custom-built circuit or a commercial hat or hardware attached on top. Transistors are used to control a large current with a small current. In this case, the Raspberry Pi is being used to control a motor through a transistor. Connecting the motor directly to the Raspberry Pi would result in too much current being pulled through the GPIO and would eventually destroy the Raspberry Pi. Instead, an NPN transistor is used to control 5 volts through the motor. This is a fairly simple circuit, and the actual components will depend on the voltages and requirements of the motor or other load. HAT is an acronym for Hardware Attached on Top, a type of expansion board that fits on top of the Raspberry Pi. There are multiple devices of this type designed to protect the Raspberry Pi GPIO from overloads. This is the WaveShare RPI relay board, and it provides 3 relays driven by the Raspberry Pi. Each relay can control a load of 5 amps at 250 volts AC or 30 volts DC. It includes opto-isolators and other handy bells and whistles. The board sells for less than $20 and comes fully assembled. Protection for GPIO output pins isn't rocket science. Simply treat them like delicate electronics. But it's helpful to be aware of things that can destroy the Raspberry Pi. Fortunately, the worst case scenario is blowing out the circuits on a Raspberry Pi and having to purchase a new one. At less than $50 per unit, that's an inexpensive lesson and not a complete tragedy. There are a couple of ways to communicate between a Raspberry Pi and an integrated circuit or a module. We've already discussed direct connections to the GPIO, the one-wire protocol, and SPI. There's another way to connect, very similar to SPI, but it's called inter-integrated circuit, or I2C. I2C isn't difficult to work with, but there are a few things you'll want to be aware of. In this project, I'll use I2C to connect the BME280 weather sensor. The BME280 is interesting in that it can be connected via either SPI or I2C. I'll also use I2C to connect a PCA9685 servo driver, which will control the servos moving the temperature and barometric pressure gauges. This looks complex, but we'll break it down into smaller parts in the following videos. So let's get started with I2C. In this video, I'll show how to connect a Raspberry Pi, a PCA9685 servo driver, and 2 servos using I2C. That's a lot of parts, but because I2C is a fairly simple interface, it's easier than you might think. I've provided a handout with all the connections written out for your reference. First, make sure there isn't any power to the Raspberry Pi. Then, connect Raspberry Pi board pin 1 to the red breadboard rail. This connects 3.3 volts DC to the breadboard. Then, connect Raspberry Pi board pin 6 to the ground rail of the breadboard. This connects ground to the breadboard. Because I'm going to be connecting 2 devices to the I2C bus, I'll bring the I2C pins to the breadboard. I'm going to place a sticky note on the breadboard so I can keep track of the pin designations. Run a jumper from board pin 5 to a breadboard row on the SCL tag. This is I2C serial clock. Next, connect board pin 3 to a breadboard row. This is going to be I2C SDA, also known as the serial data line. With those 4 lines, we can now connect the PCA9685 servo driver. Start with VCC, not V+. Connect VCC from the PCA9685 to the breadboard voltage rail. Next, connect PCA9685 ground to the breadboard ground rail. Run a jumper from the PCA9685 SCL to the breadboard SCL. And another jumper from the PCA9685 SDA to the breadboard SDA. We also need to supply 5 volts to the servos. The Raspberry Pi doesn't have enough current to drive servos, so this needs to come from a separate battery. In my case, I have a USB cord that I've prepared with jumper wires. Don't connect the battery to the USB cable just yet. First, connect the plus side of the USB jumper to the screw-down block marked V+, and note that this is different than VCC. Connect the battery ground to the screw-down block ground. Last, connect the servos. In my case, they came pre-wired to connectors. All I had to do was match the colors and push the jumpers on the pins. Connect one servo to the first set of 3 pins and the second servo to the last set of 3 pins. That's all the connections you need to make to the servo driver. In a later video, we'll run some software tests to make sure it's connected correctly. In the last video, we connected the Raspberry Pi to the breadboard and the PCA9685. Now let's connect the BME280. You'll remember how in the SPI chapter we connected the BME280 via SPI. The version of the BME280 I've purchased supports both SPI and I2C. Not all devices have both SPI and I2C. To connect the BME280 with I2C, start with the red power line connected to VCC. Check to make sure you aren't using the orange wire. Connect it to the breadboard voltage rail. Then connect the BME280 black ground to the breadboard ground. The BME280 also has a yellow SCL line. Connect that to the breadboard SCL row. And connect the blue SDA line to the SDA row. That's it. The BME280 is now connected to I2C. You'll notice the BME280 has 2 additional lines, orange and green. These are used for SPI support and aren't needed here. With the hardware all installed, let's set up the software to control these devices. Now is the time to connect power to the Raspberry Pi and let it boot up. This is also a good time to connect the 5-volt battery to the PCA9685. When the Raspberry Pi is booted up, go to Preferences, Raspberry Pi Configuration, Interfaces, and enable I2C. Now check to make sure both devices are on the I2C bus. To do that, open up a terminal window and type in sudo I2C detect -y0. You may get an error, that's okay. Also type in sudo I2C detect -y1. There's a couple of notes you'll want to take here. First of all, in my case, -y1 gave me results back, and that's what's expected. The second thing that it did is give me a couple of numbers. You can see in the line that starts with 40, there's the number 40, and the line that starts with 70, there's the number 70, and at the very end is the number 77. You'll want to make a note of the 40, and you'll also want to write down whether that is 77 or 76. It could be either one depending on your version of BME280. These numbers represent the I2C address for both the BME280, in my case, number 77, and the PCA9685, which is number 40. If you get an error message about I2C Detect not being available, you may need to install I2C Tools. To do that, go into the terminal window, type in sudo apt-get install I2C-tools, hit return, And when you've done that, you should be able to run the sudo i2c detect -y0 or -y1 commands. If you don't see both devices, check the physical connections of the devices. There is a debugging guide at www.i2c-bus.org. Be sure you enable I2C in the configuration, and did you connect SCL and SDA correctly across the BME 280, PCA 9685, and Raspberry Pi. Keep in mind that I2C is just a communication tool, like a telephone. It doesn't describe the commands necessary to control devices that are talking over I2C. To use an I2C device with Python, we'll need to install SMBus2, a library that allows Python to communicate over I2C. By the way, I'm assuming you're using Python 3. To install SMBus2, open up a terminal window, type in pip3 install SMBus2. You'll also need the BME 280 library. This tells Python how to communicate with a BME 280 module. To install that, use pip3 install R P lowercase I .bme 280. Now you can run the BME 280 test code. Go to the exercise files in Chapter 7 and run 0704 test BME280.py. I've double-clicked on this file, which will open up in Thonny, and then I can run the current script. You should see a report on the temperature, humidity, and barometric pressure. This is coming from the BME 280 and indicates that it's successfully connected to the Raspberry Pi. To test the servo, run servo.py. I've double-clicked on the file, which opens up Thonny, and then I can run the current script. This is actually a library that works with another library, PCA 9685.py, to communicate with the server controller. This will send control signals to all servos connected to the controller. In this case, there are only 2 servos connected, and they are connected to servo bank 0 and 15. When the program finds those surveys, they will step through a set of positions. If one of the servos doesn't work, check the connections. If you receive an error message regarding PCA 9685.py, be sure that that library is in the same directory as servo.py. Both PCA 9685.py and servo.py should be in the exercise files folder. With everything installed and tested, we can turn our attention to some Python code that will connect the data from the BME 280 to the servos. Let's do that in the next video. When you've checked all the parts, we're going to run code that connects the BME 280 to the servos. Open up Exercise Files Chapter 7, 0705 Servos BME 280 underbar PCA 9685. If you double-click on that, it will open up in Thonny. There are 3 parts to this program: I2C initialization, device initialization, and data gathering and interpretation. Lines 9 through 33 confirm the presence of I2C and the address of the BME 280. In an earlier video, you did this by hand with I2C detect. This code demonstrates how to find it with Python. Lines 41 through 44 then set up the PCA 9685 with the servo library. This assumes the servos are connected to the first pin set and the last pin set. Notice that the first pin set is referred to as 0 rather than 1. In line 41, you can see that the first pin set is referred to as 0, and in line 43, you can see that the last pin set is referred to as 15. It's also interesting to note that the servo setup doesn't require either the I2C bank, 0 or 1, or the ID. The PCA 9685 library assumes defaults for both of these, although you can change them if you have to set something up differently. At line 46, the program goes into an endless loop. In line 47 through 52, the program moves the servos from 0 to 180 just to indicate something is happening. In line 54, the program takes a reading from the BME 280, and then lines 56 through 63 convert the temperature to a position between 0 and 180. That servo position is then sent to the servo, which causes a servo to point to that location. Lines 66 through 74 do the same process for barometric pressure. So congratulations! You've built a weather station with a Raspberry Pi, a BME 280, a PCA 9685, and some servos. Let's take a minute to review this project. The project used several devices: a BME 280 weather sensor, a PCA 9685, and 2 servos. Like SPI, I2C allows more than one device on the bus. The weather project used 2 I2C devices, the PCA 9685 and the BME 280. The important thing about I2C is that it is one of many communication protocols, such as SPI and one-wire. I2C uses fewer control wires than SPI, but more than one-wire. But I2C isn't a complete solution. Just like SPI, it requires libraries and additional software to actually make things work. In our case, we had to install SMBus2, I2C-tools, PCA9685.py, and servo.py before Python could communicate with the respective devices. Like SPI, I2C allows more than one device on the bus. The weather project used 2 I2C devices, the PCA 9685 and the BME 280. Finally, there's a catch to I2C, but it requires a demonstration, and I'll talk more about that in the next session. I2C is a useful data communication protocol, and we've used it in the most basic ways. But there are some things to know if you plan to do more complex tasks. There are 2 complexities when working with I2C in the Raspberry Pi: device identification and I2C bus 0. Let's start with device identification. In our project, we put both the BME 280 and the PCA 9685 on the same I2C bus. So what's the problem? The problem is conflicting addresses. Earlier, we talked about SPI devices and how they use a separate pin and signal to select the chip. If you set a GPIO pin to a positive voltage, the SPI chip is enabled. In contrast, I2C depends on each device having a slave address hard-coded into the memory of the module, and those addresses need to be unique for each module. For example, you can't have 2 BME 280 modules on the same I2C bus because they have the same slave address. The Raspberry Pi doesn't know which device it's talking to, and the 2 devices don't know when to answer. In our case, the BME 280 and PCA 9685 worked together because those 2 devices have different slave addresses. We can see this with I2C detect-Y1. In this case, there are 3 I2C addresses. 40 and 70 are for the 16-channel relay driver. 77 is the BME 280. But this raises more questions. Why does the relay driver have 2 I2C addresses? Where do these addresses come from? And can these addresses be changed? Let's start with the PCA 9685 relay driver. It's actually pretty complex. Notice that both ends of the driver have a set of connectors for I2C. This is because these modules can be daisy-chained together. You can connect 62 of these boards end-to-end and control 992 servos. The first relay driver defaults to I2C address 40. If you daisy-chain additional drivers, change the slave address by shorting one or more of the I2C address contacts. This avoids conflicts. The I2C address 70 is a slave address for all call. If you send a command to this address instead of one of the slave addresses, say 40, all of the daisy chain devices will respond. For example, you could set all 62 of the servos on pin 15 to 90 degrees. But what about the BME 280? It doesn't have a bank of connectors. So can it be configured to a different slave address? And the answer is, it depends on your module. In the case of the BME 280 module I'm using, the default address is 77, shown at the very last line of the I2C detect-Y1. If I connect the orange ADDR line from the BME 280 to ground, then the default address becomes 76. Now this works for the particular implementation of the BME 280 circuit that I'm using. Different manufacturers have different methods of changing the I2C address, or possibly not at all. Okay, next question. What happened to the 0 I2C bus on the Raspberry Pi? For example, if I type in I2C detect -Y0, which polls bank 0, I get an error message. There is no bank 0. So why doesn't bank 0 work? Well, it turns out it does. Bank 0 is used to communicate with HAT, hardware attached on top, devices such as the Sense HAT. To use bank 0, a HAT must contain EEPROM with code to respond to an I2C command. You can also enable it for your own use. It involves setting up the device tree and some other modifications. This is an advanced task and way beyond what we can accomplish in this course, but it explains where bank 0 disappeared to. What we've been discussing is advanced topics and may not be immediately useful in your work with the Raspberry Pi. But it helps to understand some of the deeper parts of the technology so you can better debug situations you may find yourself facing. So far in this class, we've explored communication protocols and GPIO hardware such as I2C and SPI and OneWire. But none of these hardware tools do anything without instructions, and that's the job of software. Up until now, I've used the Python programming language, but Python is only one of the many languages available for the Raspberry Pi. Since this is a course about GPIO, I'm going to compare the most common languages you'll encounter when programming the Raspberry Pi GPIO. To help you compare and understand the different languages, I've created one circuit that I'll use for all software examples. When programmed correctly, the circuit will count to 15 in binary. When I push the button, the LEDs will all light up until I release the button. When I release the button, the count will restart at 0. I've included a handout in the exercise files that shows how to build this circuit. It's a simple project. You'll only need 4 LEDs, 4 resistors, and a push button. When you've built the circuit, I've included a Python program to test all of your connections. On the Raspberry Pi, open up 08_01_testcircuit.py. Go ahead and run this program. The program will wait until you push the button, repeatedly asking you to test it. When you push the button, you'll receive a positive message. If this first part of the program fails, check that you're using the correct GPIO pins and that the wires are securely fastened to the push button. Next, the test program will check the LEDs. First, all of the LEDs will light up for 3 seconds. Then each of the LEDs will light up, starting with the far right, then second from the right, then third, then leftmost LED. This sequence is important. If the LEDs sequence in the opposite direction or randomly, you've connected the lights wrong. If any of the LEDs don't light up, check the polarity of the LED. That's a common mistake. Each chapter in this section covers one language, and I've included finished code for each example. I'll discuss some of the features of each language, but in each one you'll see common sections. The first of those sections is Setup. Every program includes libraries and defines variables. There will be one or more subroutines to handle the lights, button, or counter. This will change depending on how a language handles interrupts, such as a button press. There will be a subroutine to convert the counter to binary and turn on the lights. I'll discuss this more in a later video. But each line takes the counter value and uses a bitwise AND, represented by the ampersand, with a binary mask. If the result is true, the LED turns on. Finally, there is a main loop that counts from 1 to 15, turns on the appropriate LEDs, and then restarts at 0. That's it. The hardware won't change from example to example, but each language has differences in syntax and implementation. Let's start with using Python to control the Raspberry Pi GPIO. You'll notice there are 2 videos dedicated to Python. This is because Python is popular, and Python provides 2 libraries. Actually, there are more than 2, but GPIO 0 and RPI.GPIO are the most popular. Now, I've provided some example code that shows how to drive the binary counter with Python and GPIO 0. We're looking at that right now. The main thing to remember about Python with the GPIO 0 library is that it focuses on buttons and LEDs instead of the actual GPIO pins. For example, in line 8, the GPIO 0 library is used to create a button. The button is called reset, and it equals gp0.button. Almost as an afterthought, that button is assigned to GPIO pin 3. Now note that this numbering is BCM numbering, not board pin 3. BCM pin 3 corresponds to the GPIO board pin 5. GPIO 0 provides some interesting additions. For example, in line 9, you'll see LED board, and that's unique to GPIO 0. LED board allows us to define a collection of LEDs and treat them as one device. In this case, the LEDS variable points to an LED board that in turn controls LEDs on BCM pins 26, 16, 20, and 21. On line 12, you'll see a function defined that shows how useful LED board is. This function, called lights on, watches the reset button. That happens in line 13. When the reset button is pressed, LEDS.on turns on all of the lights associated with the LED board pointed to by the variable LEDs. If I wanted to add an additional LED, I could just add it to the list of LEDs controlled by LED board. And when I use LEDS on, all of the LEDs will turn on, including the one I've just added. Let's look at the binary to lights function defined starting on line 21. Calling this function with a number converts it to binary and turns on the appropriate LEDs. Notice in line 22 the use of LEDS value. LEDS value sets the value of each LED in the LED board. So if I entered 1, 0, 0, 1 into LED's value, I would turn on the first and last LED. In a subsequent video, I'll describe the use of the ampersand and something called a bitwise AND. This is how the number in show this is converted to binary. In line 29 and 30, GPIO 0 with Python allows us to set up button handlers, essentially interrupts, rather than having to pull the button in a loop. Line 29 says that when the reset button is pressed, then call the lights on function. You'll recall the lights on function was defined above. While the reset button is pressed, all the LEDs are turned on. In line 30, when the reset button is released, a function called reset counter is called. I didn't talk about reset counter, but when it's called, it turns off all the LEDs and sets the counter to 0. Finally, starting at line 33, the main loop counts from 0 to 15 and sends each number to the binary to lights function. It increments the counter and sleeps for 1 second. Notice the main loop doesn't do anything with the button. In other languages, you'll see this handled differently, but with GPIO 0, button events can be watched separately from the task of counting to 15. So that's Python with GPIO 0. The advantages are that it's written in Python. It's a well-known language. It handles interrupts. It's easy to set up and use, and it has lots of under-the-hood hooks. The disadvantages to GPIO 0 are that it tends to hide direct access to the GPIO pins. For simple projects, you may not care, but for more complex hardware, you'll have to get directly to the pins. Plus, code written in GPIO 0 will have constructs specific to GPIO 0. It may be difficult to port that code to a different language or a different library. In summary, I found GPIO 0 with Python to be simple and quick. It's a great place to start experimenting with Raspberry Pi GPIO. RPI.GPIO is a code library that allows Python to communicate with the GPIO. It's been around since January of 2012 and is widely used and supported. In fact, GPIO 0 is based on RPI.GPIO. So let's take a look at how to implement code to control our binary counter circuit. In lines 4 through 13 is basic setup. We import some libraries and create a few variables. Note line 11. RPI-GPIO doesn't have an LED board construct like GPIO 0. Instead, LEDs can be stored as a Python tuple. RPI.GPIO can handle interrupts, and the functions defined in lines 16 through 27 handle these interrupts. The first, on line 16, handle reset, loops while the button returns 0. The button we have set up returns 0 if it's pressed and 1 if it's released. The not in line 17 inverts the 0 so that the button value reflects the intended logic. While the button is pressed, line 18 sets all of the LEDs to high, which will light them up. When the button is released, the button function calls reset lights and counter as defined on line 23. When this function is called, it turns all the LEDs to low so that they'll turn off. You can see that in line 25. In line 26, the counter is set to 0, and line 27 prints reset, just a helpful message to know where we are. Line 31 sets up the reset button. The code says, watch for an event, or add event detect, for the reset button, and watch for GPIO to fall. In other words, when the button is pressed, the voltage will go from 3.3 volts to 0. The opposite would be a rising voltage, going from 0 to 3.3. You'll notice there isn't any action specified for when the event happens. Instead, RPI.GPIO notices that there's been an event for the reset button and waits until it is asked about that event. This prevents events from being missed while some other piece of code is running. At line 34, an endless loop starts. In line 35, it resets the lights and counter to 0. Then in line 36, it continues to loop while the counter is less than 16. In line 37 is where a button event is handled. If the button is pressed at any time, the main loop calls handle reset to light all the LEDs and reset the counter. After checking the reset button, the main loop handles the conversion from decimal to binary, and that happens in line 40 through 43. In the other programming examples, this is a subroutine, and I could have done it the same way with RPI.GPIO, but I thought it was more understandable to use LEDs on and LEDs off, then embed the binary conversion in the loop where it was used. Because RPI.GPIO wants to use defined values such as GPIO high and GPIO low to control the output pins, I used the Python ternary operator to convert a value greater than 0 to GPIO high and any other value to GPIO low. Finally, in line 46, the loop increments the counter, and in line 47, it sleeps for 1 second before restarting the while loop testing the counter for values less than 16. So that's Python with the RPI.GPIO library. Advantages are that, well, it's written in Python, it handles interrupts, and it's easy to set up and use. The disadvantages are it might be a little bit harder to understand. In summary, I found this method to be understandable and closer to the way I think about GPIO pins. RPI.GPIO and GPIO 0 are the most common Python libraries. There's also Wiring Pi and RPIO and a host of others. Over time, you'll develop preferences depending on your project or peers. Scratch is a visual programming language where you connect code blocks to make programs. With Scratch, you can control graphics, sound, and the Raspberry Pi GPIO. Let's take a look at how to use it to control our binary counter. Open 08_04 Scratch GPIO from the example files, and Scratch will open the program and you'll see a colorful flowchart and a cat. Ignore the cat, let's focus on the Scratch program. If you need information on programming Scratch for the Raspberry Pi, please take a look at my companion course, Raspberry Pi Essential Training, specifically the video titled Use Scratch to Control the Interaction. In particular, the Essential Training video describes how to access and set up GPIO pins as input and output. I won't repeat that information here. In the code that we're looking at, you see 2 columns of code. The column on the left is the main loop, and the column on the right is a block or function that converts a decimal number to a binary and then turns on the corresponding LEDs. Let's start with the main routine on the left. The first 2 blocks, when clicked and set GPIO 3 to input, start the loop and initialize BCM pin 3 as an input. BCM pin 3 is our reset button. Before we go any further, let's see where that GPIO block came from. Go to More Blocks, add an extension. You'll see a picture of the Pi GPIO. Select it, hit OK, and then you'll notice that you have set GPIO something to output high or output low, and another block for GPIO something is high. Set GPIO something to output high allows you to send a value to a GPIO pin. GPIO something is high allows you to check the value of a GPIO pin. In our case, in the main block of code, you'll see that I've used the set GPIO with a number 3 to input. So I've set BCM pin 3 to input, and that's good because that's where our reset button is going to live. Below those two blocks is a forever loop. Inside of this loop is the program instructions to check the reset button and increment the counter. Just below the forever loop block is an instruction to set the counter to 0, and then is a repeat until counter equals 16. The first task inside the repeat until counter equals 16 loop is to set LEDs to counter. You may notice that set LEDs to is not a standard Scratch command. In fact, this is a call to the user-defined block in the right-hand column. I'll get to that in a minute, but briefly, that code takes the value of counter and turns on LEDs. Once set LEDs to counter has run, the counter is incremented by 1, change counter by 1, and the program sleeps for 1 second. Just below that is a conditional statement. If not GPIO3 is high, then, and this is what's watching the button. It's important to point out that the button has to be checked or polled. Scratch does not provide a way to handle interrupts. If the value of GPIO3 is not high, then the code inside of that conditional executes. Remember that when we push the doorbell, it drops the voltage from 3.3 volts, known as high, to 0 volts, known as low. The repeat until GPIO3 is high loop will loop checking the button to see if it's high, and if it isn't, it will use the set LED subroutine to 15, which turns on all of the lights. When the button is released, the counter is set to 0 and all of the LEDs are turned off. The loop goes back to the top of the repeat until checking if the counter is equal to 16. If not, it continues lighting up LEDs and watching for the reset button. Now, what about the code in the right-hand column? This is the code block that controls the LED. The big purple domed block at the start of the block is used to define the subroutine. You can see how it's named. Define set LEDs to, and then a number. And that number is the argument passed to this block of code. Number 1 is a variable and will contain the number that should be converted to binary. In the next line, number 1 is immediately copied into a variable called binary temp. I've done this so I can more easily follow the logic of the code. Converting a decimal number to binary and then turning on the corresponding LEDs has to be done once for each LED. So when you look at this first part of the code block, understand that it's repeated 4 times. An interesting thing about Scratch is that it doesn't have bitwise operators, and I couldn't use binary logic like I did with every other language. Instead, I've used an if-then-else statement. In the first one, the test condition checks to see if binary temp divided by 8 is greater than 1, or if binary temp divided by 8 is equal to 1. In other words, is binary temp divided by 8 greater than or equal to 1? But Scratch doesn't have an operator for greater than or equal to, so we have to string 2 statements together using an OR operator to connect the 2. So, if binary temp divided by 8 is greater than or equal to 1, then 2 things happen. First, GPIO 26 is turned on. GPIO 26 controls the least significant or smallest LED, so the least significant LED glows. Second, binary temp is set to binary temp mod 8. Mod, or modulo, is like division, but instead of returning the quotient, it returns the remainder. In contrast, if binary temp divided by 8 is not greater than or equal to 1, in other words, if binary temp divided by 8 is less than 1, the LED connected to GPIO 26 is turned off, or low. This process is repeated 3 more times, dividing by 4, then by 2. The last if-then statement just checks if the result of all the above statements leaves behind a 1 or a 0 and sets the LED accordingly. The advantages of Scratch is that it's a visual programming language. It's block-based programming, and it has a rich visual environment. And it supports threading. two operations can happen at the same time. The disadvantages are there are no interrupts, extensibility is difficult, it does not support I2C SPI or one-wire, and you're kind of trapped by the convenience. You can go as far as Scratch will give you, but you can't really go any further. In summary, Scratch is a great starting language that's easy to visually understand and explain, but there are limits, and when you reach them, it might be just as easy to switch to a different language without those limits. When you open a terminal window on the Raspberry Pi, you're presented with a command line prompt. That's Bash you're talking to. Bash is short for Born Again Shell, and you've been using it to ls a directory or cd a directory and start programs. What you may not know is that Bash has a robust scripting language that allows you to automate system management functions and to control the Raspberry Pi GPIO. In this video, let's look at how to control the Raspberry Pi GPIO from the command line with a Bash script. Running the Bash script to control GPIO requires root-level access. There are several ways to do this, but the most direct is to open a terminal window and cd to the folder that contains 08_05 bash gpio.sh. Then use sudo followed by a dot and a slash and the name of the shell script, in this case 08:05 bash gpio.sh. The dot slash says to run the program from the current folder. This will run the binary counter script, and the Raspberry Pi will behave the same as in all other languages. Let's take a look at the actual Bash code. I'm going to use the Genie editor from the programming menu in the Raspberry Pi. It starts with a line. Line 1 identifies this as a Bash script, then adds some comments and instructions. Starting at line 10, the Bash script sets up a push button. You might note this is a bit more verbose than some other languages. Essentially, Bash code or Bash shell scripts just write values into files. First in line 11, it sets up a variable called reset button and makes it equal to 3, the BCM number of the pin used to communicate with the push button. Then on line 12, it places that value into a file called export. Actually, export isn't a file. The Linux kernel recognizes this as a command to create an export path to Broadcom pin 3. But for our purposes, we can ignore that and just think of it as a file. On line 13, our script places the word in to a file called direction under the directory created for GPIO pin 3. Again, direction isn't really a file, it's a way to communicate with the Linux kernel, but we're allowed to ignore that fact. Line 16 starts the process of setting up the LEDs. I've chosen to set this up as an array rather than individual variables. You might want to do it a different way. So in line 19, the first thing I do is set up two arrays. LED pins contains a collection of the GPIO pins I'll connect to the LEDs, and the second array in line 20, LED paths, will contain pathways to those pins. Starting at line 22 is a code segment that creates the LED connections. I'm using a for loop, shown in line 23, which in Bash is notated as for, do, and then on line 29, done. For each iteration through the loop, I assign a number between 0 and 3 to LED_IDX, which will be the index into the LED pin array. On line 25, the loop prints a status message. Then on line 26, it places a BCM pin number into export. Again, export looks like a file, and we can treat it like a file, but it's really a command. Then on line 27, I capture the export path for the pin I'm creating. Finally, on line 28, I tell the system this pin will be an out pin, in contrast to being an in pin. The next segment, starting at line 31, is a function that will run when a Control-C is entered from the keyboard. It cleans up the GPIO pins I've created using the unexport file at sys/class/GPIO. On line 46 is a function that converts the value of a counter to the LED binary representation. There are 4 lines, one for each LED, lines 49, 50, 51, and 52. Let's focus on line 49, which is the line for the least significant digit and the right-hand or lower LED. There's a lot packed into this line. Looking at it from a distance, line 49, first of all, echoes a value, which is $parentheses $1 ampersand 2 pound 0001 parentheses into a file called value. Let's examine that a bit closer by starting with the value. In English, this line can be interpreted to read as the number passed to the function, $1, which is the number passed to the function, followed by an ampersand, which is and, as in a bitwise operation. And then 2 pound 0001 is the binary representation of the number 1. The result of all this will either be 0 or a number greater than 0, and that's what's stored in value. The file the value is stored into is a combination of one of the paths from the LED path array plus the word value. In this case, LED path 0 is actually /sys/class/GPIO/GPIO21 and the word value. This process is repeated for each LED by changing the binary number used with the bitwise AND equation. Finally, starting at line 55 is an endless while do done loop. In line 58, it sets a counter to 0, and in line 59, while the counter is less than 16, it tests the push button by checking the value at the path assigned to reset button. Then in line 63, if the push button is pressed, which will change the value from 1 to 0, the lights on function is called with a value of 15, which turns on all the lights. Then, starting in line 65, while the value is 0, in other words, while that button is pressed, it loops, waiting for the button to be released. In 69, when the button is released, it restarts the counter at 0, then it resumes the count, sleeps 1 second in line 73, and in line 74, it increments the counter by 1 and goes to the top of the loop. Note that if the button isn't pressed, the counter isn't reset, but instead increments by 1 until the counter is equal to 16. The advantages of Bash is that it's built-in and easily available. It's extensible. Any application that can be called from the command line can be used in a Bash script. It includes support for I2C, SPI, and OneWire, and it handles interrupts, which are defined as signals. The disadvantage is it's often overlooked as a programming language. It can be slow, and it has limited programming constructs, for example, only 2-dimensional arrays. I've personally done a lot of shell scripting, and I'm always pleasantly surprised by its capabilities. True, it does lack some advanced data structures and can be slow compared to other languages. But on the Raspberry Pi, I often don't need either complexity or speed. Bash is definitely a language worth exploring. Node-RED is a visual programming language similar to Scratch. Unlike Scratch, it's highly extensible and boasts a huge library of user-contributed modules, including I2C, SPI, and OneWire. Let's take a look at how this language works and how to use it to control the Raspberry Pi GPIO. To start Node-RED on your Raspberry Pi, go to the Programming menu and select Node-RED. This will open a terminal window, start Node-RED, and then give you the IP address pointing to the Node-RED IDE. In my case, you can see it in the upper right-hand corner. It's http://10 192.35.3.113:1880. Your numbers will probably be different. With a browser located on a different computer, open that IP address. Again, http://10.35. Don't forget the :1880 at the end of the URL, and the Node-RED IDE will display in your browser. To load the example file for this video, titled 08_06 Node-RED GPIO.json, you'll need to have it available on the same machine your browser is located on. Then go to the upper right menu, Import, Clipboard, select the file to import. In my case, my exercise files are located on the desktop, Chapter 8, and there's 08_06 Node-RED GPIO JSON. Open that, and then import that file. Now I've noticed that I have import unrecognized type counter, and I'll talk about that in just a second. What I'm going to do is click on the tab that has my program name in it, and you can immediately see that unknown counter appears. This may happen to you. Here's how to fix that. On the far right is a menu, and you'll see Manage Palette. Go to the Install tab, search for Counter, and you should see Node-RED Contribute Counter. Install that node. You'll receive a message that says the node has been added to the palette. You can close this, and if you look at the program, now you'll see that counter has been reset. So this jumble of wires and nodes is the Node-RED program for the binary counter with reset button that we've been using. Let's break it down into parts. Think of this program as having 3 points of interest: the counter, the decimal to binary converter, labeled bit mask, and the reset button. So let's take each in turn. First, the counter. This part of the program, or flow, starts with a 1-second pulse. That pulse goes to the counter, and the output from that counter goes to 2 other nodes: a reset equals true switch and the decimal to binary converter. I'll talk more about the bit mask node in a minute, but it converts the output from the counter to binary. When the output from the counter hits the count greater than 15 switch, it checks for values greater than 15. If the value is greater than 15, that switch node sends a message to the reset equals true node to reset the counter to 0. So this is the process that counts from 0 to 15. Let's look at the bit mask node. This node takes a decimal number and provides values to each of the 4 LEDs. This isn't a standard node, so I had to drag in a custom node and write some JavaScript. Here's the function block I dragged in. Double-click on the bit mask node to open the edit window. You'll see some JavaScript that includes a function called testBit with a parameter of bitmask. The testBit function takes a binary number and uses it for a bitmask to do a bitwise AND operation against the number in msg.payload. In line 2, the testBit function takes a binary number and uses it for a bitmask to do a bitwise AND operation against the number in message.payload. In line 3, if the number is greater than 0, testBit returns 1. And in line 5, if the number is 0, testBit returns 0. In lines 9, 10, 11, and 12, the JavaScript creates 4 messages, each containing the result of calling testBit with a binary bitmask. Finally, in line 14, those 4 messages are combined as an array and returned from the node. Note the outputs pop up at the bottom of the dialog. This allows for more than one value to be returned from the node. Close that dialog and look at the bitmask node. You'll see there are 4 connectors on the outbound side of the node. Those are controlled by the pop-up we just looked at. Those output connectors are then connected to GPIO output nodes, one for each LED. Those nodes come from the node palette under the Raspberry Pi pop-up. You can drag an output node from the palette to the workspace. If you open one of the nodes, you'll see a graphic allowing you to assign a pin to the node and add a descriptive name. Finally, there's a reset button. This starts with a Raspberry Pi GPIO input node from the Raspberry Pi palette. Double-click on the reset button to look inside. The reset button has been assigned to board pin 5 and set to a pull-down resistor. It's been given the name of reset button. When the button is pushed, a message is sent to 2 places. One message goes through the reset while held node, which tells the reset button to set the counter to 0. The second message tells the lights while held node to send 15 to the bitmask node. This turns all the lights on. This will continue as long as the reset button is held down. Node-RED has some great advantages. First, it's a visual programming language, again, much like Scratch, but unlike Scratch, it's readily extensible and has extensive user contributions. On the downside, the program logic for Node-RED can be somewhat unfamiliar. Flows and nodes are all foreign concepts. Lastly, concepts can get lost in some of the visuals. There's a lot of wires and a lot of nodes that appear in Node-RED, and sometimes it's difficult to tell what connects to what. I found Node-RED to be a useful language for event-driven tasks. It took me a while to understand how to successfully code solutions, but I do appreciate the way the IDE can be called from a separate platform, yet immediately run on the local machine. The C programming language has been around forever and is a must-learn language for anyone hoping for a career in computer programming. Fortunately, it's not all that hard to learn, and it's well supported on the Raspberry Pi. So let's take a look at using C to drive the Raspberry Pi GPIO. Your first task with C is to choose a library to provide GPIO access. You can access the GPIO without a library, but unless you have a specific purpose, why not lean on the hard work of one of your peers? I've done some research to help you choose a library and included a comparison table handout in the exercise files. When you look for C code examples, you'll find the Wiring Pi library is very popular. However, the author of Wiring Pi has decided to terminate support for the library and requested that people use something else. So instead, I chose the BCM 2835 library. You'll need to download and install the library. To do this, start at the airspace.com/mikem/bcm2835 website and download the tar.gz file. Unpack the file you downloaded. Now, cd to that new directory and open a terminal window in this directory so we can run some commands to make the library on your system. First, type in /configure. Then sudo make install. And that's all you need to do in order to install the BCM 2835 library. I'm going to use the Genie editor to take a look at the example file. In this case, we're looking at 08_07_C_GPIO. I'm going to fold all of the code so we can look at each line individually. Starting in line 1 are some useful commands that really aren't important. What is important is line 15, 16, 17, and 18, where we include libraries, you'll notice BCM2835.h, as well as other standard C libraries. Then in lines 23 through 36, the LEDs are assigned to pins. Note how the definitions refer to board pin numbers rather than BCM numbers. For example, BCM pin 21 is defined as RPI underbar V2 underbar GPIO underbar P1 underbar 40. In line 27, the reset button is defined. BCM 3 board pin 5. Next, on line 29, a function called lights on is defined. Briefly, we pass a number between 0 and 15 to lights on, and that number is converted to binary and used to turn on the appropriate pins. In line 38, I defined a function to handle a Control-C command. The Control-C command allows me to exit from the program. Then in line 45, we're into the main loop. In line 47, the code confirms the availability of the BCM2835 library, and then in line 50 sets up the Control-C function. In lines 53 through 56, the LED pins are set to output. In lines 59 and 61, the reset button is set to input. On line 64, a counter is defined, and an endless while loop is started in 66. Inside of the while loop, the counter is set to 0, and a second while loop is started, looping until the counter is equal to or greater than 16. While the button is pressed, lights on is called with a value of 15 to turn on all the lights. The counter is also reset to 0. This repeats until the button is released. Then, in line 70, a third while loop is started to check on the reset button. While the button is pressed, lights on is called with a value of 15 to turn on all the lights. The counter is also reset. That's line 73. This repeats until the button is released. When the button is no longer pressed, in line 76, lights on is called with the current value of the counter. Note that if the button isn't pressed, counter won't be reset until it reaches 16. After lights on, the counter is incremented, the program sleeps for 1 second, and the loop continues at the top. To compile this program, open a terminal window in the code directory, and then enter the command gcc-o bin count, which will be the name of our finished program, and we're going to compile 08 underbar 07 underbar c.gpio.c. We need to pull in -l for library, and we're going to use the BCM2835 library that we previously downloaded. To run the program, type in /bin count. This will start our binary counter program on the Raspberry Pi. So C has several advantages. First of all, if you need speed, use C. C has good library support and really good community support. The downside of C is that no attempt is made to pretty that language up. Java is a must-have language for anyone with aspirations for a career in computers. Java teaches the use of structure to keep code understandable and maintainable. Not surprisingly, Raspberry Pi provides a way to use Java to program the GPIO. Let's take a look. Your Raspberry Pi should have a copy of Java already installed, but confirm it anyways. To do that, open up a terminal window and type in dpkg --get -selections, and then a vertical bar, grep for JDK. In this case, the command returns the fact that I've got Oracle Java 8 JDK already installed on my machine, so I'm good to go. However, if you don't have Java, you'll need to install it. You can do so with sudo apt-get install Oracle-Java 8-JDK. This command will install Oracle Java 8 on your Raspberry Pi. Java requires a library to communicate with the Raspberry Pi GPIO, and the most common and popular library is Pi4J. To get it, use sudo apt-get update. That's to make sure that everything on your computer is currently up to date. And then curl -lowercase s uppercase L https://pi 4j.com/install, and then a vertical bar followed by sudo bash. This command will download and install the Pi4j library. In the exercise files folder of your Raspberry Pi, you'll find a zip file of all of the files necessary to create a Java version of our binary counter. The first step is to unpack that zip file. You'll notice that I now have a brand new 08_08 Java-GPIO folder. Open up that folder in a terminal window. Pi4j is not only a library that connects Java to the Raspberry Pi GPIO, it also provides macros to include the Pi4j library. So to compile the code, we can use Pi4j-compile. Then we look for the Java GPIO example.java source file, and to find that we go src main java com, and in my example I've used my last name, then app, and then Java GPIO example.java. Running that command will produce an executable version of the Java code. To run that command, I'll again use a macro provided by Pi4j -run. And then I give it the name of the file that I want to run. And you can see from the display that it's turning lights on. And if I press the button, it tells me that the button is pressed and turn lights on is 15. Let's take a look at the code to see what's actually happening. If I look inside 08_08 Java GPIO, I'll see source, the main, test, Java, com, Neiman Ross, app, and then finally, here is the Java GPIO example.java. I'm going to open that with Genie, a fast and lightweight IDE. And here's the Java code that actually runs the binary counter. Now, there's a lot of overhead with Java. The interesting part starts way down here. In line 76 through 79, the LEDs are assigned. Now, notice that Pi4j uses the wiring Pi numbering scheme. For example, if you're connecting to board pin 5, wiring Pi thinks of that as pin 9. Refer to the GPIO number chart for details. In line 72, we can see that the reset button is assigned to GPIO 09. Again, this is a wiring Pi number. After the LEDs and reset buttons are assigned, we now add a trigger to the reset button, and that happens in line 81. You can see reset button.add trigger. Inside of that add trigger is a while loop that checks to see if the button is low. As long as the button is low, then the system prints out the button is pressed, and it turns all the lights on by calling turn lights on with the number 15. The light counter is set to 0. When the button is high or released, it turns all the lights off. Actually, it turns lights on by sending 0, and then returns from the button handler. Independent of the reset button, the main loop, shown starting at line 95, counts to 16 and sends that value to turn lights on. After calling turn lights on, it then sleeps for 1 second and increments the light counter. It does this until light counter is equal to or greater than 16, and then it resets light counter to 0, starting over again. Now you'll notice we haven't talked about the function turn lights on just yet, but in line 110 you can see that that's where it's defined. All turn lights on takes a number, prints I'm going to turn lights on and the number that it's going to turn on. Then in lines 114, 115, 116, 117, it uses a bitwise AND operation to determine if each individual LED is turned on or off. Java has many advantages. It's speedy. It has good library support. It has amazing community support. It handles interrupts, and it has really strong variable typing to prevent making mistakes. On the downside, the file structure can be confusing, and that strong variable typing, it can be really annoying. The good news is that Raspberry Pi supports Java and supports Java GPIO manipulation. Wolfram Mathematica is a heavyweight programming language for technical computing. Scientists and researchers use Mathematica for computation and presentation of their work. And Raspberry Pi has Wolfram Mathematica included as part of the base Raspbian install. This includes the ability to control the GPIO. Let's take a look at how Mathematica does it. I'm going to jump right into the exercise files and start the exercise file for Wolfram. This is a Wolfram notebook. The first line starts with LED 1 equals 21, LED 2 equals 20, and so on. This starts by defining the pins for use by the LEDs and the reset button. These pins are then configured for output and input. Notice the use of device configure followed by GPIO. This is how the Wolfram language communicates with devices such as the Raspberry Pi GPIO. Next, a function called turn lights on is defined. Notice the use of device write followed by GPIO. This is the command used in Wolfram to send data to the GPIO. The lights on function calculates the state of the LED 4 times, once per LED. Bit AND is the command for a bitwise AND between light mask and a number. The result is tested to see if it's greater than 0, and this returns a Boolean value. The command bool, B-O-O-L-E, then converts that Boolean value to an integer, either 0 or 1. Starting with counter equals 0, the main loop begins. You'll see a do loop with a do bracket, and then at the very bottom is another bracket. At the top of the do loop, the counter is reset to 0 and a while loop is started, looping while the counter is less than 16. The first thing the while loop does is to see if the reset button is pressed. This is done with device read GPIO reset button. When the button is pressed, the value becomes 0. As long as the value is 0, turn lights on is sent the value of 15, and the counter is reset to 0. When the button is released, turn lights on is called with the current value of counter. The counter is incremented, and the loop pauses for 1 second. Note that if the button isn't pressed, the counter will continue to increment until it equals 16. At that event, the loop drops out, the counter is reset, and the while loop restarts. To run the program, click anywhere in the cell, go to Evaluation, and evaluate cells. To stop the program, go to Evaluation, abort evaluation. Wolfram Mathematica has some distinct advantages. It's commonly used by scientists and researchers. It has sophisticated data structures and large community support. On the disadvantages, some language constructs are kind of odd, and some versions are not free. Mathematica for Raspberry Pi is free, but for the industry, it's almost $3,000 a seat. In each of the examples in this chapter, I've used something called bitwise AND to convert a number from decimal to binary, and then use that value to turn on a light. My explanation in each video was brief for a reason. Logic statements like AND don't have anything to do with controlling the GPIO. Bitwise AND is a common math operation, but not a GPIO operation. So I'm including this video as an explanation of that piece of code. If you already understand bitwise AND operations, you should skip ahead to the next chapter. Before I explain bitwise AND, let's take a look at where it was used. For example, the Python rpi.gpio code. Open up 08_03 Python rpi GPIO and look at lines 40 through 43. You can see an ampersand right in the middle of the line. That's the symbol for a bitwise AND in the Python programming language. AND is an operator like addition, division, multiplication, or others. It takes one or more numbers and produces a result. With an AND operator, start with a number and another number called a mask. If the number is true and the mask is true, or 1, then the result of an AND operation is true, or 1. If either the number or the mask is false, or 0, then the result of an AND operation is false. The function of the mask is to turn the bit on or off, or, and this is important, to reveal or hide this particular bit in the number. With an AND operator, start with a number and another number called a mask. If the number is true and the mask is true, or 1, then the result of an AND operation is true, or 1. If either the number or the mask is false, or 0, then the result of an AND operation is false. The function of the mask is to turn the bit on or off, or, and this is important, to reveal or hide this particular bit in the number. How is AND used to show the binary version of a decimal number with LEDs? To answer that, let's look at the binary version of a decimal number. Here's a simple program called 0810_1 binary AND. And here's the output from that program. Imagine the binary output as 4 LEDs. An LED is off if the number is 0, or on if the number is 1. So for decimal number 13, the first light on the left would be on, the second light would be on, the third light would be off, and the fourth light would be on. You, a human, understand which LEDs would be on or off, but a computer would want this broken down into 4 steps, one for each LED. We need to split the binary number into 4 separate digits. Let's look at 0810_2 binary AND. When I run this code, you'll notice that I've added LED 8 as unknown. We need to complete the code so LED 8 equals the leftmost bit in the binary number and the state of the LED corresponding to that binary number. So for a value of 1, the leftmost binary digit is 0, so LED 8 should be off. And right now we're only interested in the leftmost bit. For decimal 15, the leftmost binary digit is 1, so LED 8 should be on. Again, we're only interested in the leftmost bit. But how do we get just that bit? Remember the AND table from above? Remember that a mask is used to show or hide a number. Look what happens when we change the number to 4 digits and the mask to 1000. I've arbitrarily selected 1000 as a mask because I want to show only the first value of the number. For each number, follow each digit vertically. The first example is 1000. The mask is 1000. So start with the 1 in the first number, then the 1 in the mask. 1 and 1 is 1, so the first number is 1. A mask value of 1000 allows the leftmost bit of the number, and only the leftmost bit, to show through. The second digit in the number is 0, and we know that both numbers need to be true for the result to be true, so the result is false. Now for any number and a mask of 1000, the result is either greater than 0 or the result is 0, depending on the first digit of the number. Here's a second example. Notice I've chosen to change the mask to 0100. This mask value will reveal the second bit and hide the first, third, and fourth bit. This time, when the second binary digit of the number is 1 or true, then the result is greater than 0. By changing the mask and checking the result for greater than 0 or 0, we can tell if the digit in the number is 1 or 0. So, in the code, change unknown to a number and 0b, this is a binary number, 1000. If you look at 08 underbar 10 underbar 3, you can see a complete solution. Do you see how the mask changes to select each of the 4 binary places? There are a couple of other notes. To see them, open 0810.4 binary and.py. In lines 4 through 7, you see a test for the left digit and a mask. If the value is greater than 0, the light is on. If the value is not greater than 0, the light is off. That's just code to show what we're talking about. And when we run that code, you'll see that LED 8 has changed from 0 or 1 to LED on or LED off. Second, you'll note that the masks in line 12, 13, and 14 have changed to decimal 4, 2, and 1. This really isn't a change, it's just substituting the binary representation of a number for the decimal representation of the same number. The AND operator doesn't care if you use decimal or binary. You'll also notice the name of the LEDs match the value of the masks, rather than a simple 1 through 4. In binary, the numbers 1, 2, 4, and 8 are the place values. Just like in decimal, the place values are 1, 10, 100, and 1000. This should give you a better idea of how the bitwise AND operator is used in the programs in this chapter. In summary, AND is an operator. AND is like other operators, plus, minus, divide, multiply. AND takes a number and a mask and then returns the positive overlap. UART, Universal Asynchronous Receiver Transmitter is available on the Raspberry Pi GPIO on board pins 8 and 10. A look at a GPIO pinout diagram shows these pins labeled as TXD and RXD. This all seems to indicate a serial data connection is available from these pins. And that's true. Well, sort of. In this project, I'll show you how to connect the Raspberry Pi UART pins to another computer. So let's take a quick look at the Raspberry Pi GPIO UART serial pins. The hardware side of UART on the Raspberry Pi is about as simple as you can get. There are only 2 pins, maybe 4, depending on your hardware. As always, before you connect anything to the Raspberry Pi GPIO, disconnect power so you don't accidentally short between a power pin and a ground pin. For this demonstration, I'm using the Adafruit USB to TTL serial cable. It combines a standard USB plug with 4 TTL serial wires. I've included a handout in the exercise files for reference to connecting these wires. Take special note of the use of the red wire coming from the USB. In this example, I am not connecting it to the GPIO. You can connect it to the GPIO, and it will supply 5 volts from the USB to the GPIO, and the Raspberry Pi will boot. But if you do this, do not connect power to the Raspberry Pi in the normal way. Notice that the white wire from the USB cable is labeled as RXD, but it connects to the GPIO pin labeled as TXD. And the green TXD line is connected to RXD. This might not be what you would expect, so be aware of the mismatch. Here's how to connect the USB UART wires to the Raspberry Pi. First of all, note that I am not going to be using the red wire. This is power, and I don't need it. I'm going to connect the black ground wire to board pin 6, which is a ground. Now I'm going to connect the white RXD line to board pin 8. Now I'm going to connect the green TXD line to Raspberry Pi board pin 10. That's all there is to it. 4 wires at max. Now let's look at the software. With UART hardware connected, we're ready to set up serial software. In this project, we'll need to set up software on both the Raspberry Pi and the laptop. Let's start with the Raspberry Pi. Go to the Raspberry Pi menu, Preferences, Raspberry Pi Configuration, then go to the Interfaces tab and enable Serial Port and Serial Console. You'll need to hit OK and then reboot. Now to establish a connection from a laptop to the Raspberry Pi. Depending on your laptop, Windows, Macintosh, or Linux, this process will differ. In my case, the device that I'm using, the USB connection, is manufactured with a Silicon Labs chipset. So I go to silabs.com to the download page, and I can find all of the drivers that I need. In my case, I'm looking for the Macintosh version, and I download the drivers that I need to talk to the USB device that I'm talking to. With the drivers installed and the USB device plugged into my laptop, I'm ready to start talking to the Raspberry Pi. To do that, I'll first of all need to find the USB device, and for that I've opened up a Macintosh terminal, and I'll type in ls/dev/cu.**. And you can see that I have 2 devices listed. One is a Bluetooth device, and the second one /dev/cu.slab_, and here's the important part, USB to UART. Your particular device may come up named differently, but what you're looking for is USB and UART. That indicates that's the device we want to talk to. To talk to that device, I'm going to use screen, which is a standard command line terminal program. And then I'm going to name the device I want to talk to, in this case, /dev/cu.slab USB to UART. And I need to specify a baud rate. And I'm going to use 115/200. When I hit return, I'll hit return and then return again. And then I get a Raspberry Pi login. This produces a screen identical to what you would see if you opened up a terminal window directly on the Raspberry Pi. So I can log in with my password. And now I can do anything that I would have done on a Raspberry Pi. This may not be immediately impressive, but keep in mind you can run programs and do any other tasks available from a Raspberry Pi command line. In your case, you'll have a lot of variables with this project. For example, the type of operating system on your laptop will change how you communicate with the Raspberry Pi. With Macintosh or Linux, you can use the screen command. With a Windows command, you'll use a terminal emulator, such as PuTTY. Or the serial device you are connecting to the Raspberry Pi may be entirely different than the USB device I've selected. The main concept with this project is communicating with the Raspberry Pi over the two serial pins. I just happen to have chosen opening a terminal window as an example of that ability. But before you start plugging in serial devices, there are some things you should consider. In the next video, I'll cover some in-depth information. At the very start of this chapter, I mentioned there were some issues with the serial connection to the Raspberry Pi. Let's spend a couple of minutes reviewing serial communication in depth. First, and very important, there is a standard serial communication protocol called RS-232. It's been around since 1960, and until recently, every computer had at least one RS-232 port, if not two. Printers, keyboards, and mice all used RS-232. It wasn't until USB appeared in 1996 that serial ports started to disappear. So you would think you could plug the Raspberry Pi GPIO serial pins directly into a printer or other RS-232 device. Not so fast. The RS-232 specification calls for voltages from negative 15 volts to positive 15 volts. And you may recall that the Raspberry Pi has a maximum voltage of plus 3.3 volts DC and a minimum voltage of 0 volts. If you connect an RS-232 connector to your Raspberry Pi, it's likely you'll send a voltage of plus 15 volts directly into the GPIO and turn your Raspberry Pi into raspberry jelly. If you need to connect a Raspberry Pi to an RS-232, you'll need a voltage converter that stands between the Raspberry Pi GPIO and the RS-232 voltages. The second thing you'll want to consider is that the Raspberry Pi GPIO is the hardware interface between two software programs, one on the Raspberry Pi and another on the receiving device. These two programs need to agree on several parameters, including speed, the size of a byte of data, are there start or stop bits, and is a parity bit being sent? Finally, it's possible to drop bits during the communication. If the outside device sends a bit to the Raspberry Pi, but the Raspberry Pi is busy with something else, it may fail to register that bit. This often happens if the transmission speed is faster than the receiving computer, or if the transmission line is noisy, say if it's next to an electrical wire. Finally, when Raspbian opens a serial port, by default, it sends the port a log-on screen and a terminal session. If the other device isn't expecting a request for password or login, it's going to be tremendously confused by the barrage of garbage characters it will receive from the Raspberry Pi. You may need to shut this behavior off so you can directly control the communication. I hope you've gained an appreciation for the tricky nature of serial communication with the Raspberry Pi, but if you need it, serial communication is available. Thanks for joining me for this exploration of the Raspberry Pi GPIO. We've talked about general purpose input and output pins, SPI, I2C, voltage levels, Zener diodes, and serial communication. We've also programmed the GPIO in Bash, C, Java, Python, Scratch, Mathematica, and Node-RED. With all of this, you now have a good understanding of how the Raspberry Pi communicates with the outside world and how you can create sophisticated projects with embedded computing for the Internet of Things. Going forward, the LinkedIn library has excellent courses on electronics, programming, and automation. I encourage you to spend time with my instructor peers to learn more about these skills. I also encourage you to subscribe to my weekly series on Raspberry Pi, where I explore interesting new technologies. And stay in touch. Please join the LinkedIn group titled Raspberry Pi Learners. I'm Mark Neiman Ross, and it's been my pleasure to teach you about the Raspberry Pi GPIO.